In this lecture, we're going to be looking at friction. So the textbook references for Halliday, Resnick and Walker for this lecture are section 6.1 and 6.2. First of all, a recap of the most important ideas that we saw in the last lecture. In the last lecture, we saw that Hooke's law described the force from a spring, and so the force from a spring can be approximated as F is equal to minus KD. Now the minus shows that it's a restoring force, which means that the force is back towards the equilibrium point. And the D, that's the distance from equilibrium. K is a spring constant. We saw that the centripetal force is a resultant force, which we kind of learnt about before, but we saw some new ways to apply it. And we saw that the other forces acting on an object travelling around a circular path add to give this centripetal force. This applies in situations such as banked curves, conical pendulums, and loop-the-loops. Okay, so we have kind of considered this question before. A mass is at rest on the inclined plane show. What is the size of the frictional force acting on the mass? So how we do it, we've got the weight force acting down, mg. We've got the normal force, which is perpendicular to the plane. And then what we can do is break the weight force into a component parallel to the plane and perpendicular to the plane. So this angle in here is theta, and so perpendicular to the plane we've got the mg cos theta, and parallel to the plane we've got the mg sine theta. Now the net force parallel to the plane must be 0. So this tells us that the frictional force must be equal to mg sine theta, as there is no net force parallel to the plane, as the mass is at rest. So static friction. The block we just saw is experiencing the static friction force, which is preventing it moving down the plane. So in order for a body to start moving, the static friction force needs to be overcome. As theta increases, eventually there is so much weight force down the slope that friction is overcome and the block starts to slide. So this maximum static friction force can be modeled as the maximum static friction force is given by mu s, which is known as the coefficient of static friction, times n, where n is the normal reaction force. So a question for you, what are the units for the coefficient of static friction? Well, hopefully you can see that this is a frictional force. So being a frictional force, it has units of newtons. The normal reaction force is also a force, and so has units newtons. So because we've got newtons here and newtons here, it means that mu s must be unitless, i.e. it does not have any units. So then we ask the question, well, which mass will start to slide down the slope first if we have a heavy mass or a light mass? We observed that, in fact, the two masses started to slide down the slope at almost the same time. So let's have a look at why that is. So here's our slope at some angle theta. We've got our mass sitting on it. Now it's right on the verge of sliding, so it's got a weight force pulling it down, which we can split into a component parallel to the slope here, which is mg sine theta, because this angle in here is theta, and perpendicular to the slope mg cos theta. And then we've got a normal reaction force, which is perpendicular to the slope. Now we know that the frictional force when it's not sliding is equal to mg sine theta. We've already discussed that this lecture. And then we've just said, well, the maximum value that the static friction force can have is given by mu s times the normal force. Now, what's the normal force equal to? Well, the block isn't accelerating up off the slope or down into the slope. So perpendicular to the slope, the forces need to be balanced. So the only forces acting on it are the weight force and the normal force and the friction force. And the friction force is parallel to the slope, so it doesn't contribute. So we must have that, well, n is equal to mg cos theta. So when we're putting in mu s n, we can put in mu s times mg cos theta. So what we're trying to do is find mu s. So let's take this part and rearrange it. And we've got, well, mu s is equal to mg sine theta divided by mg cos theta, and the mg's will cancel out. So we've got sine theta over cos theta, which is tan theta. So that tells us that the coefficient of static friction is equal to tan theta, and as you can see in this equation, there is no dependence on the mass. So that experiment told us that there was no dependence upon the mass, and the mathematics that we've just done helps to confirm that. So in this example, a 2 kilogram block is placed on a slope. The angle the slope makes with the horizontal is slowly increased from 0 degrees until theta equals 30 degrees, at which point the block starts to slide down the slope. And part 1 says what is the normal force acting on the block at this point. Okay, so let's draw a diagram like we always do. So here it is. With the weight force down the slope, we can split it into its components, mg sine theta and mg cos theta. We've got the normal force, and then we've also got the frictional force, which should be the same length as this mg sine theta. So what normal force acts on the block at this point? Well, perpendicular to the slope, the forces are balanced. So we have N is equal to mg cos theta. So we can substitute in. M is 2 kilograms, G is 9.8, and then we've got times cos 30, because it's at the point where it's just about to start sliding. And so solving this, we end up with 17 newtons for the normal force. And then part 2 says what frictional force acts on the block at this point. Well, at this point, these two are perfectly balanced, and so we have that the frictional force is equal to mg sine theta, which is equal to 2 times 9.8 times sine 30, which is equal to 9.8 newtons. And then part 3 says what is the coefficient of static friction. So this is the maximum static friction, which is equal to 9.8 newtons. We've just calculated it, and we also know it's equal to mu s times the normal force, which is equal to mu s times 17. So this tells us that mu s is equal to 9.8 newtons divided by 17 newtons, and so solving this, we get 0.58. Now, alternatively, we could have done mu s was equal to tan theta, and that's equal to tan of 30. And when we do it this way, we get the same answer, 0.58. So either of those ways works for finding our coefficient of static friction. Now, you will learn more about this in the static friction on an inclined plane laboratory exercise. Okay, now once an object starts to move, it has kinetic rather than static friction. So an object sliding over a surface experiences kinetic friction in the direction opposite to its motion. So we're asked to give an example of where you've observed this. So for example, if we push a textbook along a desk, it eventually comes to a stop because the kinetic friction is acting to oppose its motion and slow it down. So modeling kinetic friction. Kinetic friction can be modeled with the equation that the kinetic friction is equal to the coefficient of kinetic friction times the normal force. So once again, we've got a force here in newtons and a force here in newtons, so the coefficient of kinetic friction is unitless. Now, to practice using this equation for Physics 1A, try question 6 in Set 2, and the same for Higher Physics 1A. Okay, so in this question we have a block which lies on the floor, so it's just like this, and we're asked what is the magnitude of frictional force on it from the floor. Well, if it's just lying there, then there is no frictional force, so this is 0 newtons. Now, if a horizontal force of 5 newtons is now applied to the block, okay, so here it comes, 5 newtons, but the block does not move, what is the magnitude of the frictional force on it? Well, because the block's not moving, we know that the net force on the block is 0. So the frictional force must oppose this 5 newtons which is being applied. So it must have a magnitude of 5 newtons, and it'll be directed in the direction opposite to the applied force. Now, if the maximum possible magnitude of the static friction force is 10 newtons, will the block start to move if 8 newtons is applied to it horizontally? Well, no, because it won't move until a force of at least 10 newtons is applied to it. So this is no. So what would be the frictional force on the block in this case? Well, it'll still oppose the applied force, so that's still going to be 8 newtons. So would the block start to move if 12 newtons was applied to it horizontally? And in this case, there is enough force to overcome the static friction force, so it will start to move. So yes. Okay, so let's just look in a bit of detail at the transition from static friction to kinetic friction. So what we're going to do is plot a graph showing the frictional force versus time while we're steadily increasing the applied force. Okay, so initially the block doesn't move. So as we steadily increase the force, the frictional force increases to oppose this force exactly. So it increases constantly with time to some maximum value. So this maximum value is equal to mu s n. That's the maximum static friction force. Now at that point, the block is just on the verge of moving. So it now starts to move, and we have the frictional force opposing the motion, which is the kinetic friction force. So that force then remains constant with time, and this force is equal to mu kn. So generally, mu k is less than mu s. It's hard to get something moving, but once we start it moving, we don't need to apply as much force to keep it moving. So the frictional force versus time graph looks something like this. So what causes friction? Friction happens when two surfaces come in contact. So when we have very rough surfaces, then just a small amount of the surfaces are actually in contact, and so there tends to be less friction in these cases. When we have very smooth surfaces, then there's lots of surface area which is directly in contact. So we get interactions between the atoms in the two materials, and these can effectively cold weld together, so it can become very difficult to slide these objects over each other. Okay, so you've probably seen what happens to a car which is driving over an icy patch of road. Let's have a look at this example video. So you can see that the wheels have stopped turning and it's just slipping over the road, and the driver's got very little control of what's going on. So little, in fact, that they're deciding to exit their vehicle. So when a car rolls along the road, then the point of contact between the car wheel and the road is actually stationary. So we have the coefficient of static friction between the wheel and the road. When the tire stops rolling and just skids over the road, in that case we've got two moving surfaces up against each other, and so we need to apply the coefficient of kinetic friction. So let's calculate the stopping distance for these two different cases to see why we want wheels on a car to remain turning. So for a car traveling at 60 kilometers per hour, so the initial speed is equal to 60 kilometers per hour, which let's convert it into meters per second. So we can do that by dividing by 3.6, and we end up with 16.67 meters per second. We need to calculate the stopping distance if the wheels lock, and again if the wheels continue to roll. Okay, so lock, this implies that it's sliding over each other, and so we use mu k, which is equal to 0.35, and we have rolling, which means that the surface between the wheel and the road is stationary, so we've got us, which is equal to 0.70. So we're trying to get the stopping distance. So the frictional force is a constant force. So we can use our kinematic equations in this case. So we will want to use the equation v squared equals u squared plus 2as, as we know the final speed v is equal to 0 because we're trying to get the stopping distance, which is the distance it takes to come to a stop. So I've chosen the kinematic equation that has my final speed in it and also my distance in it. So we're looking at the horizontal distance in this case. So as the car comes to a stop, the only force acting upon it is the frictional force, which is working to slow it down and is given by our appropriate coefficient times the normal force. And the normal force in this case is equal to mg, as it's not on a slope or anything, we're assuming it's on a flat piece of road. So we've got that our frictional force is equal to mu times mg. So this tells us that our acceleration, ma, is equal to mu times mg. So our acceleration is equal to mu g. Okay, so we're trying to find the stopping distance. So let's rearrange this and we can write, well, s is equal to v squared minus u squared over 2a. And we've said v is equal to 0. So this is equal to minus mu squared over 2a. Now the negative, we'd expect that because this is actually decelerating it. The frictional force is slowing it down. So we'd expect the acceleration to actually be a negative number. So let's calculate this for mu k is equal to 0.35. We've got u squared, I'm leaving off the negative, times 2 times mu k times g, which is equal to 16.67 squared over 2 times 0.35 times 9.8. And solving that, I end up with 81 meters, and that's just two significant figures. Now for the rolling one, it'll be the same equation, but I'll use us. So I have s is equal to u squared over 2 mu s g, which is equal to 16.67 squared over 2 times 0.70 times g, which is equal to 40 meters, to two significant figures. So you can see when it's rolling, the stopping distance is significantly less, and this is because the coefficient of static friction is greater than the coefficient of kinetic friction. So we really want to try and keep the wheels on a car rolling so that it can stop quickly in an accident. So it's to keep the wheels rolling that engineers have developed anti-lock brake systems. So the anti-lock brake system monitors individual wheel speeds, and if a wheel starts to slow, decelerates, sooner than the other wheels, then the ABS system can monitor this and ease off the hydraulic brake pressure to the wheel so that it doesn't lock and lose the grip. So from November 2019, Australia will fall in line with the likes of Europe and Japan by mandating that all new road registerable bikes sold must be equipped with anti-lock brake systems. So this is already the rule for cars. So in effect, the new rules are harmonizing with the current EU standards, and ABS is being required in cars since back in 2003. So bikes are just catching up now. Okay, so now that we've learned a bit about friction, we're going to apply it to banked curves once again. So bank turn with friction. So the problem is a car travels around a bank curve with radius r, banked at an angle theta. The coefficient of static friction between the wheels and the road is mu s. Derive an expression for the maximum speed of the car can travel at without moving up the track. And we've got a hint. In this problem, it's easier to consider the components parallel to and perpendicular to the slope rather than horizontal and vertical, like we did in the case with no friction. Though, of course, either way will work, it's just which way is easier. So let's go with the easier way. So here's our angle theta that the track is banked at. Here's the car, it is coming out of the screen towards you. Let's draw our forces acting upon it. So we've got the weight force, mg, pulling it down. We've got the normal force, n, which is perpendicular to the track. And we've also got the frictional force, which is pushing it down the track. So that's the frictional force, which is equal to mu s times n. Now, the resultant of all these forces acting upon the car is that it undergoes the centripetal acceleration. So this red one is the resultant force, the sum of the others, and it's given by mv squared on r. Now, the normal force and the frictional force are already perpendicular and parallel to the track. Let's break these other forces into components perpendicular and parallel to the track. So here's our resultant force, mv squared on r, and we can split it into a component parallel to the track and perpendicular to the track like that. So this is our angle theta in here. This is 90 degrees. Here we've got mv squared on r cos theta, and here we've got mv squared on r sine theta. Now we'll do a similar thing for the weight force. Here's our weight force going down. We can split it into parallel to the track and perpendicular to the track. That's 90 degrees. This is theta. This is mg. So we've got mg sine theta down the track, and we've got mg cos theta up the track. So let's consider all the forces parallel to the slope. So parallel to the slope. So Newton's second law tells us that the sum of the forces is equal to the mass times the acceleration, which in this case is equal to mv squared on r cos theta, because the centripetal acceleration is the resultant acceleration. So we've got mv squared over r cos theta, which is down the slope, is equal to our frictional force, which is mu s times n, plus our weight force, which is mg sine theta down the track. Now we also need to consider what's going on perpendicular to the slope. So once again, we've got the sum of the forces is equal to the mass times the acceleration, which is the centripetal acceleration, which has got a component mv squared on r sine theta up the slope. So we've got mv squared on r sine theta, well, up, perpendicular to the slope. And we've got the normal force, which is also pushing up from the slope. And then down the slope, we've got the component of the weight force, mg cos theta. The frictional force is completely parallel to the slope, so doesn't contribute in this perpendicular direction. So we can rearrange this expression to get an expression for the normal force. The normal force is equal to the mass, which is common between these two terms here, times g cos theta, that's from this term, plus this one, which is equal to v squared on r sine theta. So we can now substitute this expression for the normal force up into this expression for the force parallel to the slope. So sub into parallel equation, and when we do that, we get mv squared on r cos theta is equal to mu s times n, which is m times g cos theta, plus v squared on r sine theta, and then we've got plus the mg sine theta. Now every term here has an m, so we can cancel out those m's to simplify it a little bit. And we can also divide through by cos theta. So if we divide this term by cos theta, we're left with 1. This one's left with 1. When we divide this by cos theta, we end up getting tan theta. And this one we're dividing by cos theta as well. So this one we also get tan theta. Now we're trying to get an expression for the maximum speed. So we want to move all the expressions with a v onto one side and the terms without onto the other. So we've got this one, which is v squared on r, and then let's move this one over to this side as well. So this is minus v squared mu s on r tan theta, which is equal to mu s g plus g tan theta. So we can put v squared on r outside of 1 minus tan theta. Sorry, I left off the mu s. It's mu s tan theta is equal to mu s g plus g tan theta. So let's go over here and simplify it a little bit more. We've got v squared on r is equal to, I'm going to pull g out the front of this one, g times mu s plus tan theta divided by 1 minus mu s tan theta, which tells me that v squared is equal to rg mu s plus tan theta over 1 minus mu s tan theta. So v is the square root of this. Okay, now it's useful just to logically check this. If mu s equals 0, then we have no friction. So we can check that this agrees with our expression from before. So in this case, we get that the maximum speed is equal to the square root of rg tan theta, because this mu s is 0, and then that's over 1. And so we end up with v squared equals rg tan theta, which is what we derived for the case with no friction. So this is at least consistent with what we derived before. So in this problem, we're told that a 5 kilogram block is pushed up a long plane inclined at an angle of 30 degrees. So let's just start by drawing our diagram. This is 30 degrees, and we've got a block here which is pushed up this incline. The coefficient of kinetic friction between the block and the plane is 0.40. So mu k is equal to 0.40, and the coefficient of static friction, mu s, is equal to 0.60. Sketch a displacement versus time, velocity versus time, and acceleration versus time graph for the block if it is originally moving up the slope at 10 meters per second. So u is equal to 10 meters per second up. And your sketch should cover the time interval until it returns to its starting position, if it does return, or reaches greatest height if not. Okay, so let's sketch our diagrams over here, and we can add to them as we work through the question. So let's make this one acceleration versus the time, and here's the velocity versus the time. So we know that the velocity is initially 10, so we can start there, and this is displacement and time, and we'll call the original displacement 0. So let's start by working out the forces that are acting upon the block. So start with forces, because they're then going to give us the acceleration, and then from the acceleration we can start to think about the velocity and the displacement. So the forces acting upon the block. Well, we've got the weight force mg pulling it down, and we can divide this into components parallel and perpendicular to the slope. That's theta there, which is 30 degrees. So down the slope we've got mg sine theta, and perpendicular to the slope we've got mg cos theta. Now we've also got a normal force which is perpendicular to the slope, and we've got the frictional force, and the frictional force always opposes the motion. So the frictional force is like this, and the frictional force, it starts off moving along the slope, so it starts off as mu k n. So let's see if we can work out n. To work out n, it's a perpendicular force. So let's consider forces perpendicular to the slope. Now we know the net force perpendicular to the slope is 0 because it's not accelerating away from the slope or down into the slope. So we've got net force equals 0, which is equal to ma, and that's equal to the sum of the forces acting. So we've got the normal force which is acting up. The frictional force doesn't have any component this way because it's all parallel to the slope, but the weight force does. So this is minus mg cos theta. So rearranging this, we can see that the normal force is equal to mg cos theta. That's rearranging that part with this part. Okay, so now we have the normal force. So now we can say, well, our frictional force, putting it back up here, is equal to mu k times mg cos theta. So now we can work out the net force parallel to the slope. So parallel to the slope, we've got the mass times the acceleration is equal to, now the weight force is pulling it down the slope, so that's minus mg sine theta. So I'm taking down the slope as my negative, and then I've also got the friction force, which is also acting down the slope. So that's equal to minus mu k mg cos theta. Now there's an m in absolutely every term, so I can cancel out the m's, and I've now got an expression for my acceleration. It's equal to minus g sine theta minus mu k g cos theta. Now I can actually evaluate what this is, because I've got values for each of these. So this is minus 9.8 times sine of 30 degrees minus mu k, which was 0.40, times 9.8 times cos of 30. And evaluating this, I end up with minus 8.3. So that's a constant acceleration down the slope. So it's constantly slowing down. And that's meters per second down the slope. But this negative here indicates that it's down the slope. Okay, so the next thing that we need to do is work out, well, that acceleration is going to slow it down. So eventually it's going to come to a rest. When it does come to rest, does it start moving again? Now, the maximum static friction force is given by mu s times n, which is equal to mu s times, we've just shown n is equal to mg cos theta, which we can substitute our numbers in. So this is equal to 0.60 times 5 times 9.8 times cos of 30, which is equal to 25.5 newtons. And that's opposing the block slipping down, so this is actually up. Now it's going to start to slide down the slope if the component of the weight force down the slope is greater than this. So we've got mg sine theta, which is equal to 5 times 9.8 times sine 30, which is equal to 24.5, and that's down the slope. So this is the weight force pulling it down, but it's not larger than the static friction force, so it doesn't overcome it. So block does not start to slide back down. Okay, so now we have an expression for the acceleration of the block. The acceleration is equal to minus 8.3 meters per second. So what we can do now is work out from the initial speed with our kinematic equations, well, how long does it accelerate for before coming to rest, which will tell us when this acceleration graph ends. So let's start with that. So we've got, there's some space here. Let's use v equals u plus at. So it comes to rest when v is 0. So we've got 0 is equal to 10 minus 8.3 times t. So rearranging this, we get t is equal to 10 divided by 8.3, which is equal to 1.2 seconds. So it comes to rest in 1.2 seconds. So if we have 1.2 seconds here, then the acceleration versus time graph is going to look like this, and this is equal to minus 8.3, and the units here are meters per second. So we've done our acceleration versus time. Now we can also substitute into this equation to get our speed. So we've got v is equal to u, which is 10 minus 8.3 t. And so this gives us an expression for the velocity. So we can see that this is aligned with a gradient of minus 8.3 and a y-intercept of 10. So if we want to sketch this one, it's going to go through 0 at this same time, 1.2 seconds. So we'll have a line like this, and then it just remains in the same place. So then it remains with the same velocity of 0. So now we just need to worry about our displacement. So to get displacement, we can use, well, s is equal to ut plus a half at squared. And so this is equal to 10t plus a half times minus 8.3 times t squared. So this is equal to 10t minus 4.15 t squared. So this is going to be a parabolic path. When we substitute in t equals 0, we get 0, which is what we expect. And when we substitute in the t equals 1.2 into this equation here, so s t equals 1.2, on the calculator we get 6.0 meters. So this tells us that the maximum displacement is 6.0 meters. And so again, it reaches that at 1.2 seconds. So here's 1.2 seconds. So at 1.2 seconds, that's going to be, I'll switch to red. That's going to be a nice straight line like that. And going up to there, you can see that it is a parabola. So it's going to look like this. Okay, so we've got a force of 20 newtons, which is acting on this block. So let's draw a free body diagram here. We've got F acting down like that, and we can break F into a vertical and a horizontal component. So this angle in here is F, and this is theta, and this is F cos theta, and this here is F sine theta. So we've got a horizontal component F cos theta and a vertical component F sine theta. Now other forces acting, we've got the weight force, which is acting vertically down. We've got the normal force, which is acting vertically up. And then we've got the frictional force, which is going to be opposing this applied force here. And the coefficient of static friction is equal to 0.50, and the coefficient of kinetic friction is equal to 0.30. But at this point, we don't know if it's going to start moving or not, so we don't know which one we're going to need to use. So it asks, what is the frictional force on the block? So to work out the frictional force, we're going to need to consider the horizontal forces. So horizontally, we've got that the net force, MA, is equal to, well, we've got this F, which is pushing it to the right. So we've got F cos theta to the right, and then minus the frictional force, which is to the left. But we don't know with the friction quite how to calculate it yet. We don't know which of these to use. So let's calculate maximum static friction force. So the maximum static friction force is given by mu s times n. So we're going to need to know what this normal force is, but we don't have that yet. So to get the normal force, we're going to need to consider what's happening vertically. So vertically, we know that there is no net force because the block isn't accelerating up or accelerating down. So we've got ma is equal to 0, and we've got the normal force going up. We've got the F sine theta going down, and then we've got the mg going down as well. So this tells us that the normal force is equal to mg plus F sine theta. So we can substitute that into our maximum frictional force here, and we've got mu s times mg plus F sine theta. Now what we can do is we can actually evaluate this, because we've got mu s is 0.50, m is 10, g is 9.8, that's plus f, which is 20, times sine 30. And we can evaluate this on the calculator and get 54 newtons. So if we're pushing it with more than 54 newtons, it will start to slide. So how much are we actually pushing it with? Well, we're pushing it with just this horizontal component here, the F cos theta. So we can say, well, F cos theta is equal to 20 times cos of 30. And when we calculate that, we get 17.3 newtons. So we're pushing it with this to the right. So that's not enough to overcome the static friction. So not enough to overcome static friction, which tells us that our block doesn't move. So horizontally, this acceleration is equal to 0. And so our frictional force is just equal to the F cos theta, which we've calculated here. So the frictional force is equal to 17 newtons, and that's to the left, opposing this applied force.